All right, thanks, and welcome you all to today's Zoominar on waves and sound. Before I introduce our wonderful speaker for today, we'll have a quick reminder that this meeting will be recorded and will be posted at some point on YouTube for those who couldn't attend or tune in today, or those that may want to revisit this content at some point. With that, it is my pleasure to introduce Professor James Thomson, a senior principal oceanographer at the University of Washington's Applied Physics Laboratory. James studies waves, currents, and turbulence by combining field observations and remote sensing technique. And we'll be discussing his recent work on wave development, bubbles, and ambient sound in the ocean. Before I hand over to James to start, I want to make this quick announcement that we're still looking for speakers for this current year, Zoominars, and we please ask that you volunteer yourself or suggest someone by sending us an email via this address shown on your screen. With that, I will stop sharing and Tim can take over.
Okay, I'll bring this up. Does that look good?
Looks good.
Yeah. Okay, well, I have to start with an advertisement for WISE, for in-person WISE, not the webinar, but the WISE meeting that is usually every spring. We will host in Seattle next year or this coming year. And here's some information. Really the only thing you really need is this website here. So sites.uw.edu WISE 2025. This should have everything you need. It has these tabs at the top and you can look. There's nothing on the agenda yet, of course, but a little bit of information about the location, the lodging, registration, etc. And then some links that are broader WISE links. So working on putting together the last of the details right now, and we'll open the registration and abstract submission the beginning of December. And that'll be open through until the end of January. We're going to try something different this year where you register and submit abstracts at the same time, all at once. So it should just be one transaction and then done. And we'll release the agenda later. For those of you who like to wait and see whether you were given a poster or a talk before you register, too bad. You just register when you submit the abstract. We'll find a spot for you somehow. And if you really want to give a talk, we are going to have a session that is entirely based on null results. And by that, I mean things that did not work, so that we as a community do a better job of starting to talk about the dead ends that we find and the things that don't work, because those don't usually get published. And then I think they end up getting repeated. So I would like to start talking about them, and I will try a session of null results and see how it goes. Here are the actual dates. This is a Monday, Tuesday, Wednesday, Thursday. So it would arrive, I recommend you arrive on the 11th, which is a Sunday, and we'll have a social hour that night. And then these are the 4 days of the actual meeting. Okay, any questions on that? I'm very happy at the end or anytime you can reach out to me with questions about this. But just want to make everyone aware and use the opportunity to advertise for WISE 2025. Other very important thing is we have a firm limit of 100 people for in-person attendance. So registration will open and the first 100, that's it. And the room cannot hold any more, and it's a strict rule from the fire department. So it's a safety issue. We cannot have more than 100. Beyond 100, we will have everything available to watch on Zoom, but just to watch on Zoom, not to present. So if you want to present and be in person, don't wait on your registration because we have a limit of 100. Okay, now for the talk today. I'm going to tell you about wave development and ambient sound. This is a paper I've been working on with all of these co-authors, and thankfully a few of these co-authors are actually underwater acousticians, because I am not. And so I have sort of just stumbled in and started working with some data, and can freely admit that I don't have all the expertise to understand what I'm looking at in the data sets, and I've really appreciated having some of these acousticians involved. It's been a fun collaboration, and there are lots of analogies between ocean surface waves and acoustic waves, but there are also lots of key differences, and there's some language differences that are remarkable. Even though we're all English-speaking scientists working in a physical science, we still have some different ways of talking about things. There's a preprint available of this work. It was just revised and resubmitted. It's in version 2. I will freely admit that version 2 is a lot simpler than version 1. There were some really big things in the review that I addressed and made a much simpler paper. And think I kind of got out in front of my skis a little bit on version 1. So what you're going to see today is pretty simple, but I hope it's useful. And what we're starting with here at the opening slide is a picture of just below the ocean surface of the bubbles that are formed during wave breaking. And I think that's key to this overall process, as I'll try to explain. Okay, so first, my crash course in ambient noise in the ocean was learning about wind noise, so what's called wind noise. So as I understand it, the state of the art for decades have been these Wentz curves. This was originally done in the 60s, a seminal publication by Wentz, and they have these spectral levels. So this is the sound level in dB, and this is the acoustic frequency. So it goes up to many kilohertz. And this is what the sound spectra in the ocean look like. They've got a region off in the low frequency here that has a lot of ship noise and seismic activity. And then there's a region here in kind of the mid frequencies that is, say, 1 to 20 kilohertz, which is within the band of human hearing. And there are these different spectral levels here that are a strong function of the wind speed. Wentz notes that it's really bubbles and sea spray, but talks about them as wind noise. And the convention for a very long time has just been to call this wind noise. So if you're looking at ambient sound, 1 to 20 kilohertz, people say, oh, that's wind noise, and it scales with the wind speed. So much so that some work has used ambient sound measurements to infer the wind speed, right? You can put a hydrophone on a profiling float, and even though that float is below the surface, you can infer what the wind speed is at the surface by how loud it is. And that's why it's called wind noise. But of course, it's not really the wind, right? When you look at a picture like this from a ship in the open ocean when it's very windy and rough out, it's all of these breaking waves and that's what's actually making sound, right? It really is a wave-driven process. The wind is the forcing function, absolutely. But my question has been, what are the details to this wave-breaking process that are affecting how much sound is produced? And basically, can we update some of the things that have been done classically in the literature with wind noise to make it wind and wave noise, or even wave breaking noise, something more physics? And I have to know there has plenty of people have had this idea and worked on this. There's a lot of work by David Farmer throughout the 80s and some in Ken Melville's group through the 90s. There was a nice paper by Felizardo and Melville that related wave dissipation to ambient noise. So now that's a lot closer tied to wave breaking, right? But not much that has ended up in a parametric form that's easy to use and just say, well, if I have this sound level, that's what it means in terms of wind and wave. Or the other way around, like if I measure this amount of wind, what sound level should I expect? So that's where I'm going with this. Okay, so what do we know about wave breaking, winds and waves making whitecaps and making breaking? I'm just going to give you a quick review that is somewhat narrow, admittedly narrow, of what we know about whitecapping at the ocean surface. There's hundreds of papers on this, so don't be offended if I cite the wrong thing, including just citing some of our own papers, because that's an easy place to find the figure you're thinking of. So first, we know about whitecap coverage. So W is the percent by area of the amount of surface that has active foam on it, indicating whitecaps. There's been a ton of work on this, all these papers here with lots of different fits, as whitecap coverage as a function of wind speed. That's the conventional thing to do. And it's usually something kind of cubic like this. There are a bunch of different fits to the data. There's a scatter, but whitecap coverage goes up with wind speed. Okay, we know that. We've known that for a long time, and that is the reason it makes sense to talk about wind noise when you're talking about wave breaking, because it's so closely correlated to the wind. The amount of breaking, as indicated by whitecaps, is tied to the wind. Great. But it's also tied to the waves, and we know that too. And there are several papers trying to make better connections between this W whitecap coverage and the wave conditions. Here's an example where we tried doing the peak wave steepness. So this is now whitecap coverage and then a bulk indicator of steepness, so significant wave height, and then the first moment wave length, and divided by 2 for a steepness estimate. And certainly there's correlation, but there's also a lot of scatter, and some power laws in the literature work okay on a different data set, but it's not perfect. But we can be a bit more nuanced than that and use a spectral steepness, or use the mean square slope, and that's what's shown here. So this is again whitecap coverage as a function of the mean square slope. So this is the 4th moment of the spectrum. It is showing us the steepness in the tail of the wave spectrum, which I think is really where a lot of the breaking activity is happening, and it's probably a more representative, and it's also broadband, right? It's capturing many scales instead of being stuck at one scale like the peak metric is, and it has better correlation basically. And this so this shows us that white capping is a wave and wind driven process. Well, let's take this a little further and talk about scales. What scales are breaking? One of the ways to look at that is to, or one of the reasons you would look at that is look at the spectrum. So we know plenty about this, right? There's been lots of work on equilibrium spectra. So here's the plot is a whole bunch of wave spectra as a function of frequency, colored by wind speed. This is 2 years of data from an open ocean site at Station Papa. And you see that in the spectral tail, the equilibrium shape of f to the minus 5.4 that we expect from Phillips and other publications, that is really universally observed, and it's very well sorted by wind speed. And this is the region in which we dynamically expect the wave action balance that's written down here, that any change here is small, and it's a balance of the wind input term, the wave breaking losses, and the nonlinear transfers within this part of the spectrum. And it should have this shape. So this is a proxy indication that wave breaking should be happening at these smaller scales. This is where a lot of the wave breaking activity should be. And these are the scales at which you would set that mean square slope metric that I was using before. So this is where we think a lot of the activity is. And the peak matters somewhat, but is not as directly involved. We could be a bit more specific about that and look at the lambdas. So the lambdas are the breaking crest distributions. If you're not familiar with this metric, the idea is that the total length of crests that are breaking at the sea surface can be partitioned in this way. Lambda of c is the length at any speed. So it's a distribution of crest lengths, and the distribution is a function of speed. It's almost like a spectrum of crest lengths. And speed lets you look at scale, lets you know what scale the breaking crests are at. So here's a smattering of things from the literature. There's also a lot of a very deep literature on using lambda of c, but I just want to use it as a metric for what scales are breaking. And one way we can look at that is to normalize the c, the speed of the breakers, by the peak phase speed. So each of these plots does that from different publications, different data sets. There's lambda, so this is basically use that as a proxy for breaking activity. It's a function of speed over breaking speed. And each of the plots is, from different publications, but basically the same. And for each of these, you see that almost all of the activity is at a value that is less than 1, right? That's what you see here, that's what you see here, and that's what you see here. So that means these are speeds that are slower than the peak, and slower means shorter waves, right? Just from deep water dispersion, right? So there is, a logarithmic scale here, has hardly any breaking above the peak phase speed. So hardly any breaking at scales longer than the peak, and most of the breaking at scales much shorter than peak. Maybe at 1/2 of CP, something like that. That's been observed a fair bit. Sometimes it's broader than that, but the overall idea is that the breaking is happening at small scales. And that's really the takeaway from this part of the literature, is that the breaking is a wind and wave driven process, and it's preferentially at the smaller scales of the waves, something smaller than the peak. Okay, what about the bubbles themselves? We know that so wave breaking makes bubbles. What do we know about the bubbles? The bubbles are what, in their initial active phase, they're the things that resonate and ring, and they make the sound, or they pulsate. I think resonate's not quite the right word, according to reviewer 2. They pulsate, and but they make sound. They make sound right in their initial phase, and then after that, they hang around for a while. And there's a lot of ways to quantify this. This is an image that's taken from a buoy just below the surface, and you can see all these different bubbles. And there's been a lot of work on this recently. This has been a really active area recently, in part just trying to figure out how deep do these bubbles go? What's the length scale on the vertical? So I'll just walk you through a little bit of the literature. And again, I'm not capturing everything, but there was this paper by Strands et al. In 2020. They have a really long time series, over a year of data from a site with an ADCP that they use as an echo sounder, and they trace the acoustic backscatter to look at the bubble plume depth, and they're also using an EK60 echo sounder to do that. So very, fine resolution when they do this. And they look at it as a function of wind speed. So the bubbles are deeper at higher wind speeds. Makes sense. They're quite deep. They're 10 to 15 meters deep, which is a lot, I think. The max bubble depth is even up to 30 meters in some cases. And it's tightly correlated with winds, but also well correlated with the height of the wind sea. So this is not the total HS, but the height of the wind sea. And you can see that the bubble depths, the dimensional depths are often greater than the wave heights themselves. So these are wave heights of, these are wave heights of a few meters, 3, 4, 5 meters, when bubble plume depths that are 10 meters. So more than the wave height themselves, which I think is interesting and relevant. There's this very recent paper, and this is from the Southern Ocean data set, and they're looking at a similar set of metrics with how deep these bubbles go. So this is, again, bubble plume depth, just different notation as a function of wind speed. Less tightly correlated by wind speed, but some ideas, can be many meters, and certainly is a function of wind speed. And then also as a function of wave height, and again, correlated, but some scatter. So the wave heights are in the mix, but not uniquely a determinant. And then I see Alviso's here. Here's this recent paper done at, I think, at the Aqua Alta Tower, tracing with sonars, echograms, these bubble plume depths like this, and some, pretty similar results in a lot of ways. These are several meters that these plumes make it down. And then they have these persistent timescales where, this is several minutes, right, that a bubble plume will come down and then be persistent for a long time. And to be this persistent, the bubbles have to be very small. So these bubbles are no longer actively producing sound, but they still matter because these small persistent bubbles, they can actually attenuate the sound. They can, and then effectively, if you are a receiver, receiving sound at depth below this, you'd actually receive less sound below all these persistent bubbles. So this is an important thing that is was known in the literature, but is emerging as a really robust result from more papers like this. And in a very recent publication, this one here, Zapata et al., and they're again looking at how deep do the bubbles go, many meters as a function of wind speed. The data from that data set, well correlated with wind speed, but some scatter, and then comparing to a bunch of things. We also, in the group here at UW, have done a similar study, and I've just spent a little bit of time on that because it's relevant to what I'm trying to do here. So it's this paper, the Durakti et al., the paper Morteza led, and we were using our Swift buoys with a Nortec Signature 1000 looking down from the buoy, using it to do different pings for echograms and for broadband Doppler profiles and for pulse coherent Doppler profiles. And here we're just using the echograms. And if you look down 30 meters and do some thresholding, you see that over the course of several minutes, you get events like this where there's a little bit of breaking and there's some bubbles, and then there's a really vigorous breaking activity, and there are bubbles that come down, and they make it to 20 or 30 meters depth, similar to these other studies. And then what we have done in this paper is make a distinction between what we threshold for what we think are the really active bubbles, and these are the ones that are right here, these bubbles. So we're calling those the very active bubbles. And what happens with these passive bubbles, which are this cloud, these persistent bubbles back here. The idea being that these ones, the active ones, are the ones that form right at breaking and are responsible for sound generation. And these persistent bubbles are the ones that they stick around a lot longer, many wave periods, many minutes, because they're so small. They don't have a strong rise velocity. They don't have much buoyancy. They're fairly passive in the hydrodynamic sense. They just go along for the ride with the turbulent motions in the upper ocean, and they stick around for a while before they eventually collapse or dissolve. We went through all this data, and Morteza came up with these similar scalings as a function of wind speed. Here, these are bubble plume depths normalized by wave height, and it looks at these different trends in terms of everything's increasing with wind speed. But there's a difference between what the active bubbles do and what the persistent bubbles do. And that difference becomes more exaggerated at high winds. Okay, so that's a little bit of a very quick introduction of what I think sort of the state of the art is in our understanding of how waves evolve through breaking, and that breaking is quantified, and what scales the breaking is occurring at, and then the bubbles that are produced by that. A lot of that still has a ton of empiricism and just, pure observations and empirical fits in it, but it gives us this picture that the wave breaking is, of course, very strongly tied to the wind. It is happening at the smaller scales of the wave spectrum, and then that drives all these bubbles that are in the upper ocean, and at times at pretty significant depths, 10, 20, 30 meters, even if the H sig might only be 5 or 10 meters. So my overall question and the idea behind this work is to say, can we improve the classic wind noise parameterizations with some wave information? Can we do something better? So I'm going to walk you through first a case study trying to develop this, and then use a big data set to make it statistically robust, because the case study is really kind of a one-off and not sufficient for that. Okay, so the case study comes from the Norwegian Sea. So here's Norway, Sweden, Iceland, and this little island, this volcanic outcrop of Jan Mayen, this little island there. This is part of a project that has run the last several years called NORSE, and it stands for Northern Ocean Rapid Surface Evolution. So in this project, we are looking throughout this whole domain and watching big fall storms come across and see how the upper ocean responds. And there has been some work by a group of acousticians to understand sort of the 3D soundscape here and how sound is propagating in and amongst all this bathymetry and the strong stratification and all sorts of, there's a lot of oceanography happening here. But we ended up with a simple case study that I'll explore here that I think just shows the wave development or the wave related part. And the case study happens behind the island of Jan Mayen for a single event. So this is the volcanic island. It's a pretty tall island, and therefore it makes a pretty good wind block. So there was an event where the wind was coming strongly from the northwest, and the ship put out a bunch of buoys that are these marks here, and then the ship went and hid behind the island. Why did the ship hide behind the island? Well, because it was going to be very rough and a little bit dangerous, and because behind the island the waves are very small because there's no fetch behind the island, right? The island blocks the waves, and so the waves have to sort of regenerate afresh from here. And now, of course, there's some refraction and diffraction around the island, but this is a safe place to hide, and the ship could ride out the storm. That will become relevant. So here are the buoys we put out. These are the swift buoys that we make here. And in this experiment, we've toyed around with adding hydrophones to them. So usually they just look like this. You have met station, acoustic Dopplers here, temperature, salinity, GPS, IMU for wave spectra, those kind of things. Here we added this tether that is a bungee cord, not shown, but there's a small damping plate here to try to isolate the motion. And then the compliance of the bungee cord isolates it further. And then there's a hydrophone down here, and the one we're using is made by a company called Loggerhead, and it's called the Snap, and it can record, can sample it up to 300 kilohertz. And this is totally internally recording, so it's only mechanically coupled and isolated. There's no data from here up to here. We have to recover this to get the data back. Okay, so there's this event, and the wind's coming from over here, and we put 4 of these buoys out. 2 of them have hydrophones. The red one and the yellow one have hydrophones, and we're going to look at the difference between those 2. Here's the time series. I'm only looking at a few hours here. U10, the wind speed for this event, is 18 meters per second, basically across the board. All 4 buoys measure 18 meter per second winds at their locations for the peak of this storm at all locations. But the wave heights are different. Of course, the wave heights are different. It's a fetch limited condition right behind the island. So this red buoy behind the island measures smaller waves. So if I rotate this and make myself a local coordinate system, then the island is at 0, 0, and the distance behind the island in kilometers looks like this, and the wave heights look like this. So the red buoy only measures HS of 2 meters, and these buoys measure 4 meters. So there's definitely fetch limitation happening down here. So again, wind this way, fetch limitation. Well, the spectrum gives you the measured wave spectrum gives you a much more clear picture of that. So again, the red one is the one in here, and the orange one is the one here. So the thing that is very telling to me is that both have the same equilibrium range. This is that F to the -4 equilibrium range. This is where braking should be balancing wind input and balancing nonlinear transfers. And these should have the same level in the tail here. It's the same wind speed, right? This is why companies like SOFAR can infer wind speed from their spotter buoys just from the waves alone, because this tail is set by the local wind speed, and that's it. That's the end of the story. It's a local process. This is a local thing. But the peak is not a local thing. The peak is something that has accumulated energy as the wave field has matured, and that needs space and or time, right? You need to either fetch or you need time to accumulate the wind input from here to here, and then you end up with this wave field that's in yellow here. So it makes a lot of sense that this peak is much larger here. It's a whole decade larger. It has shifted to the left, so the peak frequency is longer, lower than the one is here. All of that makes sense. And then there's nothing really at low frequencies. This also suggests there's not much energy getting around the island, right? There's not really maybe there's a small peak here, but there's not something that's clearly wrapping around the island and arriving at that red location. It is basically a fetch limited pure wind sea just behind the island. And then here, the orange line, or yellow orange, I will argue that that is a almost fully developed wind sea, that it's at very long fetch and almost not seeing a fetch limitation anymore. Okay, that's what's in the spectra. Let's just go to the classic analysis here. This goes back to World War II. This is a very old analysis where we just look at the non-dimensional wave height. So H hat is non-dimensional, and it's non-dimensionalized by the gravity and wave height, and the dimensional wave height, and then the wind speed squared. And that works out pretty well. If I look at non-dimensional fetch, non-dimensionalized in the same way as a function of non-dimensional wave height, then I end up with a bunch of different values, because I do this for several hours as the storm goes. The ones right behind the island, they kind of lie right on this canonical line here. And then the other ones, they're close, they're not exact. And the gray bars here are this is the range of literature values for this dependence. So, in general, we should have this parametric dependence where there's more non-dimensional wave height at non-dimensional fetch. There's scatter. This buoy is actually, slightly off axis from these other ones, but I think it's pretty close. So these blue and purple buoys, they only have wave and wind measurements. They don't have the hydrophones. So that's why they appear here in the wave analysis, but they don't appear in the acoustic analysis. Okay, so hopefully I've convinced you very simply that there's fetch limitation happening at this site, and it has a strong relation to what scales are in the wave spectrum. So now, I talk about bearing the lead. Now let me show you how this is related to sound. Here's the measured sound spectra. This is the ambient sound measured by the hydrophones as a function of acoustic frequency. So now this is kilohertz, not hertz. And across the board, the red sound spectrum is louder than the yellow sound spectrum. There's a couple little details in here. There's this dashed line here where the hydrophone has a notch in its response that we calibrated after the fact in some controlled tests. And so we extrapolate across this little frequency band here that's in the appendix. I wouldn't worry about it, but just that's why that's dashed there. But the rest of this is a pretty robust measurement. And it's louder at short fetch. That might be a little counterintuitive at first. Why is it louder at short fetch? That's certainly not in these Wenz curves, right? The Wenz idea is it should just be the wind. These have exactly the same wind. It is 18 meters per second measured at these sites by these buoys. So there's not some question of, oh, the ship was measuring over here and there's different winds over here. No, these are the winds that were measured by the buoys. It's 18 meters per second at both sites. So why is it louder at one and not the other? The Wenz curve would say it's just the wind, so they should be the same, but they're not. Well, here's a hypothesis, is that it's related to this. So they have the same wind, they have the same equilibrium range, but they have differences at the peak. Well, what does that mean? I think it's related to these scales. So here's my little cartoon. Rather than do a lot of math, I'm going to give you simple pictures. And a cartoon is that in a cross-section view of a wave, that the short waves are the ones that are doing most of the whitecap, right? The lambdas we were talking about from the literature, they're all wave scales that are less than the peak wave scale. But then there are these long waves, maybe even swell in some conditions. Here, there's not really, you can't call it swell, but there are very fully developed waves. And then these longer, larger waves. And those are the things that set h sig, right? If I step back to the spectrum, there is a tremendous amount of energy, integrating under this curve. So these might have the same levels in the tail, but the total HS of this orange line, it's really dominated by all this energy at the peak. That's energy and things that are happening in kinematics at the ocean surface that have a lot to do with the peak, but aren't directly related to braking, right? The braking is happening at these short scales, and then there's this larger scale that is setting the HS. Well, the idea is that if we go back to this picture, that this part, the small scales, that's the active bubbles, that's sound production. This longer scale here, where the persistent bubbles are able to penetrate to a few multiples of the significant wave height, 1, 2, or 3, depending on the data set you're looking at, those persistent bubbles, those are the ones that caused sound attenuation. Sound is made up here when an active breaker occurs, and that's a pretty brief process and very episodic. And then the sound propagates down to depth where your hydrophone's down here somewhere. And on its way, as it propagates, there are all these losses at the surface, and that's related to these persistent bubbles. So here's my very simple idea, is that this classic good old metric for wave development, which is the non-dimensional wave height, HS over U10, has something to do with sound attenuation, which is this scale here, this long scale of the attenuating bubbles relative to sound generation. And that really is mostly a wind-driven thing. These are because the wind and the short waves that do all the braking, that control the equilibrium range of the spectrum, they're all pretty much in local lockstep with the wind. But HS doesn't have to be. HS can have been developing as over the duration and fetch of a developing wave field. And this HS, this is a thing that provides a kinematic mechanism to just homogenize this layer and to provide transport. And we see empirically that if you're looking at these persistent attenuating bubbles, that they have a correlation with HS, even though HS is not really the relevant metric for braking. U10 is the relevant metric for braking. So what I'm testing out is this idea that we can use wave development as an additional control on the ambient sound, and this is the logic behind it. So if I go back here, so why would it be louder at short fetch? At short fetch, there is all the wave breaking is happening, and there's a small HS. There's not much of an attenuating layer. At longer fetch, orange, there's the same amount of wave breaking happening. So sound production is the same, but the layer is thicker that does the attenuating. So there is less sound received down at the receiver that's at depth, because that sound is propagating through a thicker layer, and that layer is from HS. So that's the idea that wave development is what's controlling these two things. They have the same wind, they have the same wave breaking, but they have a different H sig, and that different H sig is a thing that is attenuating sound. Okay, so here's my little schematic for what these, how to interpret these, right? These simple wave development metrics, non-dimensional wave heights. Classically, if it's less than 0.15, then these are waves that are fetch limited and they're still developing. And I'm going to generalize it and not really talk about fetch limitation anymore, because this limitation can also be a duration limitation. You can just not have enough time to build the wave field. So it's underdeveloped or still developing if this is less than 0.15. And that means that these short waves that are doing a lot of the braking, and the equilibrium range is really most of the spectrum. The equilibrium range dominates the spectrum. Once you get to 0.15, the wave spectrum is fully developed. We can argue a lot about the nuance of that, but you have a really fully developed peak at that point. And now H sig is really coming from the peak of the spectrum, and these small scale waves are doing most of the braking. They're not the biggest contribution to H sig anymore. The peak is really the biggest contribution. And then, of course, we always have to allow for, you can get way above this if you have swell, because swell is coming in from somewhere else, right? It's a remote source. It's not local. So you can have, this could really at some point become infinite, right? You could have almost zero wind and a strong swell, and then this would just absolutely blow up. So let's just leave open for that case. All right, so now let's actually test this idea, because the case study, is it's not inconsistent with this, but it's not much data. So we have worked at Station Papa for a very long time. Here I am in Seattle. Here And here Station Papa is out in this is the Gulf of Alaska. So it's sort of the bottom of the Gulf of Alaska. It's about halfway between Seattle and the Aleutian Island chain over here. And there's a long-term measurement station there. There was a weather ship there during World War II. And then there have been repeat measurements there by Canadian colleagues for a very long time. And a surface mooring there in 2007 onward, and then a wave rider buoy, a data well wave rider that we added in 2010 and have maintained since then. And all this data is available through the CDIP program at the Scripps Institute of Oceanography. If you're looking for that data, that's the best place to find it. So sometimes when we put out that mooring, we've put out a hydrophone on the same mooring at depth, again, mechanically isolated. So I have 2 years of data where I've got a hydrophone right below the wave mooring, and then nearby I have another mooring that's measuring wind. So I have all the things I need to test this and test it robustly over 2 years. Here's an example of the time series. Here's the hydrophone data. This is, so frequency again in kilohertz, because this is acoustics, over 2 years, July to July, again to July, and the sound level in dB. And you can see it has all these kind of striping here, and that striping is related to the wind speed. That's the next panel, and then the wave height. And there's this seasonal cycle where, you know, there's big winds and waves in the winter, and then it's calm in the summer, and then big winds and waves in the winter. And we have a lot of dynamic range. What we don't have is any fetch limitation, right? This is 1,100 nautical miles from Seattle to Station Papa. So there's definitely no fetch limitation here, but there still can be underdeveloped waves. If the wind changes quickly and shifts quickly, then there's time, it takes time for the wave field to adjust and develop. So there can be duration limitation. So if I go back to that very simple metric for wave development, it can still be applied here. And that's what is in this panel here, that simple non-dimensional wave height. Well, here's a joint PDF of all the data from those 2 years every hour. So the wave heights and the wind speed. And the fully developed waves would lie along this curve. And anything less than that are actively developing waves. Not necessarily because of fetch limitation, but because of duration limitation, or because they just haven't finished developing yet. So these would be the ones where the equilibrium range really dominates the spectrum. And anything here, this is where the peak is really well developed, and then, you know, further out here, then there must be some swell coming in from somewhere else, and, you know, providing more total wave activity than the wind would support. Okay, so got a big data set that I can test things on, and then I can ask, how loud is it at the hydrophone below the mooring? And remember that what I'm expecting is it's a strong function of wind speed. So it is definitely a strong function of wind speed. This is the ambient sound level at a particular frequency band, 6.5 kilohertz. And this is the wind speed. It increases with wind speed just as expected. But if I subset the data and I look at developing versus fully developed waves, and then I ask, is there a difference between these two? Then I see that they are separated. The developing ones are louder and the fully developed ones are quieter. Apologies, I'm just realizing this is an old version of this plot. This has the wrong error bars on it. You'll have to believe me when I tell you that when I put the right error bars on, they actually do separate, and these two populations are statistically significant, not just at the 95% level, but actually at the 99% level. So it's an old version of the plot. You'll just have to take my word for that. Anyway, my point is that there is a difference between the wind speed dependence for developing and fully developed. So stepping back, it's still mostly the wind that controls the ambient noise, but there is this subtle adjustment. How much? A few dB that is between whether the waves are developing or not developing. And I think the mechanism could be that it's not a change in how the sound is produced, but it's a change in how the sound is attenuated as it gets down to the receiver at depth, because that attenuating layer of persistent bubbles is scaling with total wave height or total wave activity. And that's more just a kinematic thing. Now I can try to generalize this and make something that looks like the Wentz curves. So the Wentz curves are sound spectra as a function of frequency, and there are all these different colors or different lines for the different wind speeds. So what Wentz would usually do is merge the dashed and undashed lines. So there would just be one color red for 21 meter per second, one color orange for 15 meter per second, et cetera, et cetera. I've taken those Wentz-like curves and I've separated them into two different populations. They're solid if the waves are actively developing, and they're dashed if they're already full developed. And this shows a generalization of the plot we were looking at before, that it is across all the frequencies in this kind of wind noise band. It's always louder when the waves are developing relative to when the waves are fully developed. And that happens at each of these wind speeds. So if you think of these as Wentz curves, what I'm proposing is a modest adjustment to the Wentz curves. And if I look at it as a function of frequency and ask what really is that adjustment, what's the delta F? Here's a direct plot of that. I'm just going through and subtracting the dash from the dotted, and then I take an average over all of them, and I get 2 or 3 dB. So 2 or 3 dB is the difference at a given wind speed for whether it's developing or fully developed. So those of you like me who are not acousticians should immediately ask your acoustic colleagues, does it matter? Does 2 or 3 dB, is that an appreciable amount? If I tell you I can improve your ambient noise predictions for whatever your application is in the open ocean by a couple dB, are you excited or not? And the answer I've had so far is that yes, it's worthwhile, it's good to do, because there's still a lot of scatter in the Wentz curves. That for any one of these curves, like let's take the 21 meter per second curve here, that normally wouldn't be partitioned by waves at all, it would just be wind alone, that has scatter within that wind speed bin that is several dB itself. So I'm talking about an adjustment that based on waves that is basically the same as taking you from one wind speed bin into the neighboring wind speed bin. So I think that is appreciable, right? That, you know, what the waves are doing and how they're developing is the same as having winds that are a bit greater or a bit smaller on the order of several meters per second. So I think it's appreciable, or it's something that can improve the skill level in our predictions or interpretation of ambient sound, a few dB. Okay, yeah, so there's a box with it. There's a takeaway. At a given wind speed, the ocean is 2 to 3 dB quieter once the waves are fully developed, and I think that's more about sound attenuation than it is about sound generation. All right, I'm gonna wrap up soon, don't worry, but first I want to just show you one fun thing for this audience that I was playing around with in the paper, and then it died in review, but I still think I might be worth playing with at some point. This is the really classic non-dimensional wave height, right? This has been in the literature since the 40s. And I was thinking, well, you know, we could do other things with this, because we can estimate the wind friction velocity from the wave spectrum itself, right? This is how, so far in the spotter buoys, give you a wind estimate from the buoys. They're looking at the equilibrium range and making this relation based on Phillips 85 for what the wind friction velocity would be. So and we know this is related to the mean square slope of the wave spectrum. Well, that means we really can write wave development, this h hat, as a function of mean square slope. Now we have something that's entirely defined by the wave spectrum, right? It's really just a ratio of the fourth moment of the spectrum to the first moment of the spectrum. Or I said it backwards, but you know, square root of the first moment of the spectrum to the square of the fourth moment of the spectrum. That's this ratio, and that we can interpret as you know, a ratio of the energies in the different partitions of the wave spectrum. You could think of it that way. You could think of it as good old wave development. You could think of it a lot of different ways. So I started playing around with that from the Station Papa data set. And it had some interesting things. Again, I'll go back to this collection of all these spectra. Wave energy is function of frequency. Here's the equilibrium range. Looks like we expect. It sorts by wind speed as we expect. That's why this stuff works over here. And then if I make this new metric and I ask, how does that compare to the old metric? This is the new one, it's the old one. They're certainly correlated. They do, go together, but they're different. And all that really says to me is that maybe this is something we could use in the future that's purely wave driven. Certainly you could use it when you don't have a wind speed estimate. You could use this. And maybe it may be useful at the very lowest winds, lower winds, where there's a ton of scatter between these two metrics. And maybe this is something that might be more dynamically relevant. As the wind speed gets really higher, they tend to collapse together. So that's just a fun thing to think about. Yeah, it didn't end up in the paper, but it might carry it forward somewhere. Okay, I'm going to conclude. Sound generation is by active bubbles. It's tied to whitecaps. We already know that, but I'm just emphasizing that's mostly a short scale process. Sound attenuation, I think, is by persistent bubbles tied to larger scales. Some of that's definitely well known too in the acoustics literature, back to papers from the 80s. But this connection to which wave scales, control how deep those bubbles get and how thick that layer is in the vertical, I think that's a somewhat new thing to apply. So if I use this classic and very simple metric for wave development, it seems to separate populations of the sound levels at a given wind speed. So it's a modest adjustment on the existing state of the art. And the answer is it's 2 to 3 dB quieter once the waves are fully developed, because I think that layer has gotten thick. All right, the very last thing, I'll just end with, that's my last slide, but I added an epilogue because I gave a seminar recently that had nothing to do with waves and sea ice. And afterwards, someone told me they were disappointed in me. So I don't want to disappoint you. So certainly all this stuff happens in sea ice. Here's an example of the Arctic from a couple years ago with a big amount of open water, and this varies seasonally a ton, right? This is what it looks like at the end of the summer season, and there's all this open water and not much ice left. And then of course the ice will advance throughout the fall and into the winter, and this will be totally ice covered in the winter, and then it'll open up again next summer. And we know that opening and closing of open water dramatically changes the wave conditions in the region. And we have lots of papers on how fetch limitation is a big part of the dynamics in the Arctic. So, would we see these kind of effects measuring acoustics in the Arctic? Absolutely, I think we'd see it. In fact, I think it's one of the best places to go looking for it. I just don't have much of that data yet, but we do have some fun new projects with using fiber optic cables for distributed acoustic sensing. So here's a paper by Michael Baker using a fiber optic cable that extends 35 kilometers in horizontal, and he's looking at the spectra as ice forms along this cable and seeing that it starts to get quieter and quieter and quieter as ice covers the whole cable. And I think that's related to all of these processes. And definitely there's a spatial part of this here, right? There's a fetch limited part of this as the ice comes in, and there's lots of fun acoustics here. There's also a lot of noise that the ice itself makes and changes to the propagation as the ice is changing stratification. It's complicated, but I think it's another place where these things will likely matter, and it's one of the things I'd like to do next with all this. Okay, I'm going to end with another advertisement for WISE. I hope you come join us in Seattle in 2025, and I hope you don't wait until the last minute to submit, because we might hit that upper limit of 100 people, and then you would have to be watching on Zoom from somewhere else. And I would love to take questions. Thanks.
Great. Thanks for the wonderful talk. If you have any questions for Jim, now is the time. Good.
There's one in the chat. Can I just take that right away?
Okay.
From Danielle. Yes, she is absolutely right that that the depth at which the sound is measured matters, but it usually, so these are all depth adjusted and corrected, but it doesn't matter as much as I originally thought. I had to learn this stuff, but that if your hydrophone's shallow, then the cone you're receiving from is kind of small, and as the hydrophone gets deeper, then the cone you're receiving from gets deeper. So first order, a lot of hydrophone measurements of ambient noise at different depths are actually pretty comparable. But Jay Yang helped me, make sure everything was adjusted for depth. So we are aware of that, and we did do that. Thank you for that question, Danielle.
Great. Other questions?
Can I make one, Bernard?
Yeah.
Hi, Jim. Thank you for the seminar. Very interesting results. Just an opinion about how relevant for you is the Langmuir circulation in pushing the smaller bubble down and then eventually attenuate the sounds in your case. So it's not only HS at that point, but something more complicated.
Definitely.
And
yes,
the second part, as you are also dealing with the observation, is there a way to observe Langmuir some way? Now to figure it out?
That's a great question. I should have said more about it. This very recent paper talks about Langmuir and looks at the Langmuir number and how deep the bubbles get, and kind of finds some preferential extent based on Langmuir. I mean, some of these other papers have talked about it too. I think it's absolutely relevant. Definitely. I mean, you get strong Langmuir circulations, you get these vertical transport mechanisms, and I think it absolutely matters. I tested it in the Papa data set, and it didn't reveal a lot, but we have had a similar issue in the Papa data set historically looking for Langmuir. It's that it's such an open ocean case that that we don't have a big range of Langmuir numbers at Papa, basically. It's a pretty narrow range compared to the rest of what's in the literature, so it hasn't been the best place to look for Langmuir effects in general. But I think it's definitely important. I think it's yet another wave-driven process, right? We're back to a different ratio. It's the Langmuir number is the ratio of U star friction velocity to U Stokes, and there's another place where like the getting away from this assumption that the winds and the waves are just absolutely have a one-to-one correspondence. That I think that's my biggest message to the acousticians in this work is stop doing that, right? All the wind speed based things have just assumed, well, the waves are just, at 10 meters per second, there's only one way the waves can be. Like, well, no, there's all sorts of, things that can happen at 10 meter winds, 10 meter per second winds. And the variations in Langmuir circulation is another big one that provide a lot of transport. How to measure it was the second part of your question.
Yes.
We have been working on it with the Swift buoys some, which is a bit of a sampling bias problem, right? The buoys, they're freely drifting and they're buoyant, so they always end up at the convergences. So if you put them out in a random field, they end up accumulating, right at the downwelling spots. And we do see downwelling. We see downwelling that is well correlated. So W bar is correlated with the turbulent Langmuir number, and you get things that are 15, 20 centimeters per second ensemble average vertical velocities. It's pretty strong. It's pretty remarkable. So that's one metric, but then you're not seeing the whole field, right? You're just seeing like, this is what it is right at the downwelling part. But I think it's an important mechanism. I think it's, and when you look at that, then you're suddenly not surprised you get bubbles down to 30 meters in some of these cases, or even 40 meters, right? Because you have a strong transport mechanism. It might be not spatially homogeneous, it might be really concentrated in regions, but it'll carry that stuff down. Should have had a slide on Langmuir.
Yeah, so in some cases, we also argued that dense water formation is important to bring bubbles, but also it happens in a few places around the globe. So for instance, where we have other towers, it can happen. So in those cases, the downward velocity that can help bubble to be brought.
We just got a data set last year in the Labrador Sea. It was a thing with Helen Chursky and a bunch of other folks. And I think we see, Labrador Sea, definitely you get these dense water formations. And I think we see some pretty remarkable bubble excursions downward that it might be related to that.
Thank you.
Other questions? So you have 3 minutes.
Could I ask one, Bernard?
Okay.
Thanks a lot, Jim, for your talk. Very nice. Could you explain again, and maybe I missed it, the physical mechanism that leads to the scaling of the attenuation layer with HS? Is there a physical mechanism that causes that scaling?
It's mostly empirical. That's mostly what we see in some of these data sets. I do think, HS does set the scale of the orbital motions in the vertical, right? That's just, those orbital motions are just A omega. They are irrotational at first order. They can't do any work, right? If they're not braking, they're just, they're just orbits, right? But that is an advection mechanism, right? You're sort of, just in those orbits alone, you're homogenizing well, it depends on which reference frame you're working at, but you're homogenizing a layer of about HS, and then HS is just a representative scale. There are waves that are bigger than that and smaller than that and multi-scale. So I think it might just be mostly advection.
Yeah, just linear velocities and advection. Okay.
Yeah, that's it. Yeah. Why? I'm not going to come up with anything fancier than that if the simple explanation might be it. Yeah.
Makes sense. Thank you.
Great. Any last question?
May I add one last question?
Okay.
I'm not sure I got the right information. What is the sampling frequency you used to get your acoustic measurements?
Pretty sure we were 80 kilohertz. So we didn't do that. Those hydrophones can do 300 kilohertz, but then you run out of space for a long experiment. So I think we were recording at maybe it's 82 or 80, but I think I remember the Nyquist is about 40. And for the wind noise, we're interested up until about 20 or 25. So that was fine. That was far enough. Yeah.
Okay, thank
But-
you.
But you missed some of the dolphins that way, I think.
Great. So thanks everyone for tuning in for the meeting. Hope to see you the next. Watch out for announcements. With that, we thank our speaker and we'll end the meeting.
Thank you. Thank you very much, Jim.
Thank you very
Very
much.
interesting.
See you in
Bye-bye.
May or before.
Or before.
Yeah.